So good morning, students. Hello.
Good morning, ma'am.
So are you able to hear me clearly?
Yes, yes, ma'am.
Because I'm using two devices, one for audio, one for sharing your MATLAB window. Okay. So we'll wait for 2-3 minutes and then we'll start. Okay. Good morning, students. Are you listening? Everybody is listening? Hello? 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 Am I audible?
Yes, ma'am.
So we'll start. So this is fourth experiment. Here we are going to just see the modeling of your cruise control system. Okay. So very simple model we are considering. So we are trying to represent this your vehicle dynamics in the form of some equation. Okay. So how that particular equation can be represented? What are the factors that we are going to consider to represent your vehicle dynamics? That we'll see first, and then how it can be implemented in your MATLAB. Okay. So basically we are going to See, we are going to model cruise control system. So what do you mean by cruise control is you are setting the speed of your vehicle. The reference point will be set. Okay. And irrespective of whether you are driving on the hills or whether you are driving on the slope or whatever are the disturbances in your driving, so your vehicle is supposed to drive or it should run at the constant speed. That is the concept of your cruise control. Okay, so this everybody knows. Okay, so in short, what we are trying to achieve is we are trying to achieve constant speed irrespective of all the disturbances those are occurring. Okay, so automatically your system should adjust to the speed variances or the disturbances those are occurring. For example, you are just driving on the just on a surface which is not or you are driving continuously on the highway and suddenly there comes some bridge, and whenever you are climbing or driving on that bridge, so we need to reduce usually speed. Okay, we cannot drive with the same speed, but when we are using or your vehicle is in the cruise control mode, okay, so it should uh, even though you are trying to drive or the vehicle is just gone on the sleep, okay, so it should maintain the constant speed. So how it can be possible using our Simulink model, that we'll see. We are not considering other parameters like whether there exists some vehicle in front of that or something. So that everything comes under your adaptive cruise control. Here we are simply saying it's a cruise control considering only one vehicle and considering the dynamics corresponding to only one vehicle which is in the motion. Okay, so how it can be modeled or how it can be how to obtain the transfer function or differential equation corresponding to this particular vehicle. Okay, and finally the aim is to get the constant velocity speed for that particular object, or that is vehicle in our case. Okay, so to move your vehicle there has to be some force generated. Okay, so we are considering that force, okay, which is in the direction of the movement of your vehicle. Okay, so total force which is responsible to move your object is always, or it is always the force, the actual force that has been generated by the engine, the power that has been generated by the engine, minus the frictional forces or the frictional losses that are occurring. So your vehicle is moving in this direction, so air velocity or some frictional forces between your vehicle and road, okay, so those are represented by this factor B. Okay, so which is known as frictional constant, and that is always opposing to the speed with which your vehicle is moving. So the total force is can be equated to the actual force minus whatever are the losses or the opposition, the uh, factors those are opposing the velocity, the speed of that particular vehicle. Okay, so we are getting this particular equation, whereas this force is nothing but the force which is responsible to move your vehicle, and that can be represented in the form of mass into acceleration, which is represented here as mass dv by dt. Okay, so just now considering this part of the equation, what we'll get is finally we are interested in the velocity. So output of this particular system is speed and input is the force that has been applied or that is responsible to move your vehicle with that speed. Okay, so this is acting as the input and velocity is acting as the output. So this is the differential equation that we are getting, where m is representing mass of this vehicle and b is the fractional friction coefficient, okay, for that particular vehicle which is opposing the velocity, okay, which is trying to it is always in the opposite direction of the force which is responsible to move your vehicle in a particular direction. Okay, so this is what is the simple equation that we are getting if we consider the Laplace transform form, or we are interested in obtaining the transfer function to implement this particular vehicle model in MATLAB. We are interested in the transfer function of that system, or either you can go with this particular equation, differential equation. As yesterday we have seen how to build the differential equation in the MATLAB. Again, we'll continue that in the regular lectures. Okay, but same way, either you can implement the differential form of equation, okay, or you can go with this transfer function. So it's easier to implement or use the transfer function to represent your vehicle. Okay, and hence the transfer function can be obtained by converting your differential equation into Laplace form. This is representing the Laplace form. As just we have discussed, we are interested in the speed which we want to be constant, okay, all the time, and input that is responsible to drive with that particular speed is nothing but force. So this output is velocity or the speed of the vehicle, input is the force applied to that vehicle. So this is representing your output by input, which is giving us the required transfer function. So this is the required transfer function 1 upon ms plus b, where m is representing mass of the vehicle, weight of that vehicle, and b is representing the frictional coefficient. Okay, the resistance that is opposing the velocity. Okay, so with this particular equation, now we can model. It's very simple. It is representing your first order equation, first order transfer function. So this, that means your vehicle, a simple vehicle dynamics can be represented using first order transfer function, and the same function we are going to implement to represent your cruise control. Okay, so is this clear? The transfer function to represent your vehicle. Is there any doubt? Yes, everybody is listening, or you're busy in some other work?
No, ma'am.
Only Akshay respond. Sometimes Akhilesh. What about others?
Listening, ma'am.
Listening, everybody. Yesterday I called
Yes, ma'am.
Mallar, not answered 2-3 times. Ishita also. Are you there? Ishita? Rishabh? Listening? Part. Okay. So this is just explained how we can represent your vehicle model. Okay. So using that vehicle model, now we will start with the Simulink. So as we have discussed and implemented last time also, one of the design. So Simulink design, or to implement your model in Simulink, you have to open that Simulink window. So that can be opened by just simply typing the Simulink. Okay. So when you type the Simulink, or you can use this icon, might be in your MATLAB version. It has some other notation, or location will be somewhere else. But you may find this Simulink library icon on this toolbar. Okay. So you can directly click on this Simulink library, or you can type this to open your uh, Simulink library explorer or browser. Okay, so we can go through this file, new model. Okay, so through this model you can create, or here we can create the new model. So our vehicle model, we are directly going to use the transfer function. So I'll just show you we are going to implement here three different cases. One is simply the vehicle model, the ideal condition where there are no disturbances, nothing is coming in between your vehicle and the driving of that vehicle. Okay, and in that case, we are getting the expected set velocity. Okay, so for that, how it can be represented? I think I'll go with. Okay, I'll show you 4 steps for only one, and rest 2 designs I will share with you directly. Okay, so basically we have to represent that vehicle model which we are representing using the transfer function, and input to that system is force. So force will be represented in the form of gain. Okay, so I will simply add the subsystem first representing your vehicle model. Okay, so subsystem block. So this is giving subsystem right add to untitled. Okay, so I have added this subsystem to this. Now I am just removing and adding our vehicle dynamics model. What we need in this is the transfer function block. So this is the transfer function we want. We are implementing our system in the continuous time. Okay, so we are using this. How to make your design discretize, that will study in the class. We will show you one of the design that is converted to a discrete time. So here we will use this. You can either you can just press and drag and drop that particular thing here. Okay, and apart from this, I need the input, which is the gain block. So you can search those. So this is the gain block I want. Okay, so this is representing your internal system, and we will simply connect these two. Okay, so for our design, we will consider mass as 1000. Okay, so these are the coefficients of your S and this one. So here we will replace these coefficients as 1000. So if you are not getting at any point, you can stop me and ask. Okay, so what is the transfer function that we have obtained is 1 upon ms plus b. So that m value we are considered as 1000 and b value will consider as the 50. Okay, so these values we have set. How we have set those values? By simply double clicking on this transfer function block. Okay, and just change the coefficient values to 1000 and 50, representing the coefficient of your S and the constant 1. So instead of 1, that is B, the friction coefficient or the friction factor that we are getting. So once you set this, click on OK. And gain we have to set as, it is the force which is responsible to drive your vehicle. Okay. Now, in our model, we are trying to represent the throttle angle, okay, which is responsible to generate based on the throttle position. So how we are representing is simply your pi by 6 we are considering as the factor, that is 30 degrees are represented as the only 30 degrees are your throttle plate is open through 30 degrees. Okay, and with that, so 1000 is the gain that we are considering, and pi by 6, pi can be represented as this. So this factor is representing the gain block or the force that is responsible to get our output velocity, that is speed. Okay, so on speed we are just the expected speed is 20 meter per second. So you tell me how much kilometer per hour that will give us if the speed is set to 20 meter per second. So with these settings, we are trying to get the output as 20 meter per second as the speed of that vehicle. Okay, so the same thing can be represented as 6000 by pi. Okay, so instead of 1000 by pi by 6, I'm writing that as 6000 by pi. Apply that. So gain will be set to 6000 by pi. Okay, and this is representing your subsystem, that is vehicle model. So this is my vehicle model. Okay, so this vehicle model, now I'll apply this step input function, and output we will observe on the just output will observe on the scope. Okay. So in this sense, you can get that scope, floating scope or this scope. Okay. So I'll just put this input, step input representing the throttle angle. Based on that throttle angle, your gain will be set representing force to the vehicle to your transfer function. Okay, or that transfer function is representing system. Okay, and expected output that means. Okay, so the throttle angle step time is, you can change after what time duration, after how many steps, after how many samples you want to change the value which is initially 0 to the final set value. So that is representing your set time. So I'll consider that as 5, and final value will consider it as pi by 6. So it will be represented as pi by 6. Okay. Expecting, representing, we are representing that, or we are assuming that as the throttle angle. Okay, with this settings, so you have to change this if you want. Okay, so this is actually what I said is you need to configure your model. So model configure, usually fixed step we can go for here because we are not using any optimization and anything. So stop time, whatever you set there, you can see here also. So if we are not interested in all the solver options, so you can directly change the stop time period. Okay, so this is representing the number of steps, or the 100,000 seconds it is representing basically. So time is in the second. So you just apply that one and click on OK. Okay. So we have set that to 1000. And now I'll simulate your model. Okay. So this is actually, we are getting that as, see here. So your output is, we are getting till 1000, so that is not applied. I'll change that time duration. Okay, so this is the response time at this step time, or after 5 seconds, your input had changed to the expected, or that degree, or the throttle angle has been set, and for that particular throttle angle position we are getting this response. Okay, I'll increase the time duration so that you'll come to know exactly what is happening here. Okay, so this is the 1000, and then I'll simulate it and just double click. Okay, it's not changing. I have simulated again, and so if we just now I have changed this, we are getting that up to, I'll change the axis properties so that you can clearly visible your graph. Okay, so this is what is expected. We are expecting constant 20 meter per second output, and that we have obtained using our model. Okay, and this is considered as the idle model where there are no disturbances. Okay, so getting initially this is the response time we are getting. So some time it is taking to obtain that required speed. Okay, so that time duration is, it is approximately 100 seconds it is taking to reach to the expected set value. So this is what is expected and that we have obtained. But this is what this system is representing. So this system is representing your open loop system. And whenever we are driving in an open loop system, there are many disturbances which are occurring. What is the disturbance? Suppose your vehicle is moving on the hill, okay, or the just slope on the slope. So there is some the factor of that force is just getting resolved, or it is being activated in the downward direction. So that is represented as your MGH, mass, gravitational force, and whatever is the height. Height can be obtained using your sine theta. So that particular component we can obtain. Now, once how to build this model, I have shown how to include the subsystem. Okay. So for those subsystems, so this is representing your internal vehicle model. So just when you click on this up, we are getting the actual model where input is connected and output can be observed. Okay. So same way, now we'll add in our design. So I have already built the remaining two. So this is representing here. I have considered that gain also separately. Okay. Whereas this is representing your subsystem. Okay. This is gain simply. Whereas in our system, this your vehicle is getting, you can create two different things, a single model. So I have combined these two into single. Okay. So considering this as the gain block and this as the transfer function for your vehicle model. Okay. So this is representing your vehicle model. Okay. And this is the gain. That is nothing but the input force which is responsible to drive this vehicle model. Okay. And as I said, it is never this ideal case. There are some disturbances, and those disturbances we are representing using this, again another step function we have used to represent that steps, the disturbance, and that is represented after this step time 100 seconds. Okay. So our final value, so or whatever are the disturbances or that step value, the disturbance value is represented as mg sine of theta. Okay, the slope is considered at your vehicle is just dived on a slope of 45 degrees. Okay, so that is represented here by sine pi by 45. Okay. So this is the component, or this is the force that is getting resolved, or this is the disturbance which is responsible to reduce your speed of the vehicle. So whenever such disturbances are occurring while driving, so what is the response of your, or how will be the response, or what is the change in the speed in this particular system that will observe. Okay. Only what we have added in the previous system is the disturbance that is represented as, now vehicle, instead of just driving on the same surface, the continuous surface without any slope, now it has suddenly taken on to some slope. Okay. So that is represented by this particular model. Okay. So I have simulated this one, and you can just see now the change. Okay. So disturbance has been set after 100 seconds. So after 100 seconds, instead of 20 meter per second, suddenly the speed has been reduced because the vehicle is driving on the slope. So it couldn't maintain the required speed, the required set point, that what we have assumed initially is 20 meter per second. So that is not possible to achieve because your system is representing the open loop system, which is not stable. So it is becoming unstable. It is to just drive or to maintain your vehicle dynamics. It is reducing the speed. Okay, for all those settings, whatever are the initial values we have provided. Okay, now how this particular thing can overcome. Okay, so or how, irrespective of all these disturbances, how we can maintain the required speed, that we'll see. Okay, so that is possible by getting the feedback, by reading the actual speed at every instance of time and just comparing that speed with the required set point. So this set point, this step function is representing the what is the expected speed of your vehicle, and this particular line, this feedback line is representing the actual speed that we are getting. So it will obtain the error between the actual point and the set point, the reference speed or the expected speed and the actual speed, and that error will be given to PID. So yesterday we have started with this controller. The job of this controller is it will adjust the error, or it will try to compensate the error and provide the required input to your system. Okay. So whatever is the reduction in the speed because of this disturbance has been occurred, so that will be reduced because of this PID controller. So how to get this PID controller is you can again find that component here. So if you just write here PID controller, you will get this PID of S we are getting because we are using continuous time system. We are modeling continuous time system. Okay. So this block, I'll just delete this and again put that block here. Okay, because it might be tuned previously. Okay, so I'll add this to CC and so I'll just put that PID controller. Okay, with this the previous observation we have seen, because of the disturbances our speed has been reduced after 10 seconds. Okay, now same settings are here after 100 seconds, not 10, 100 seconds. The same disturbances are added here. Okay, same system. This is the gain whose values are 6000 by pi. Okay, just go up. This is representing the transfer function with 1050 instead of now one signal. This is representing your gain is applied here, and second one is the disturbance input is getting applied. So you need to add those two signals to this transfer function. The same block is implemented in this open loop system. Okay, here. So two inputs will be added, and so actually your input force is getting added with the disturbances, and that is connected to the input of the transfer system that is representing your vehicle. Okay, and output is obtained from that. So this is representing your subsystem vehicle model, and finally we are trying to get now constant. Our objective is to get constant speed from that particular system. Okay, now I'll simply reduce and we'll see what will be the changes or how we are getting those. What is this? Okay, I'll just check this. This is after 5 seconds. The final expected value is 20. Okay, so gain is set as 6000 by pi. Okay, so just one step. This is correct. Here it is. Everything is correct. Okay, so I'll simulate this. I'll save this model first and then simulate. So this is something that we are getting here. Okay, so this is input I think this is input we are getting and this is the output. Now see here, we are not getting the expected value. So how to obtain that expected value? For that, you can just click on this PID controller, okay? And you have to simply, here there are two options. You can select continuous time, discrete time analysis. We are using continuous time, so continuous time. This is the PID controller. So this one is either you can use that PID configuration. So all these three blocks in parallel, or it can be idle, means it may be giving you series combination. Okay. So you have to simply click on this tune, which was not initially linear. We are not getting the linear curve at the output. So your plant will just linearize that output. It will try to get the expected output, expected speed. Okay. So it will take some time. So directly it is giving us the required time response. Okay. See, this one is giving us tuned one, and this was the block response, but we are not able to see this block response initially. Okay, so I'll check this. Okay, now we are tuning. So either we can update this block. What this is particularly representing, you can change the response time. Actually, this dotted line is representing our previous response. And this is representing better response actually. But we were not able to see in that output. I'll check again what was the problem. But this is what is the tuned by the system. Okay, so it has been automatically tuned, and the differences you can just check here. Okay, so what this is representing, these are the PID values, the proportional constant, integral constant, and differential constant. So these are the three values for the tuned curve. So this is the tuned response. Okay, and these are the values before tuning. So where the proportional constant is 1, integral was 1, and this differential was 0. Okay, and here you can observe all those analysis parameters. What is the rise time? What is the settling time? What is the overshoot? Okay, so I'll just first without or simply by just changing, you can tune this one. Okay, so you can see how we can tune or how the parameters are changing. So rise time in this is reducing. You can see as I just move this slider of the response time. Okay, so transient behavior also, with this you can just change the steady state error. There is change in the steady state error with this. Okay, so this is something we can obtain, or this is how you can tune using these two waveforms. Okay, so this is giving us better, and actually our previous one was better. We can go back to that one, but if you are not getting the proper response, so how we can obtain that? By tuning this one. And after tuning, if you are getting the expected, you can just click on this update block. Okay, so it will update, your tuned values will be set to the block values. And after this, I'll simply close this one. We have tuned our PID controller to minimize the error that is resulting into decrease in the speed. And with this settings, I'll again execute our model. Okay, so it is ready, and here we can observe now something is going wrong. Okay, I will just remove that input so that we'll come to know which one is okay. Okay, I'll run this one. I wanted to actually change inputs to 1 only. So I have executed, and this is what. So this is representing your input. I'll add another scope and then we'll check. I'll save this model and I'll execute. And we are interested in the output of this, which is giving me something simple. Whereas in PID controller, we are getting actually the required output. So why it is happening so? So something is going wrong here. See here, the block output is nothing but the output of our system it represents. Actually, this is the response. This is the block response, and this is the tuned one. Okay. So this block response is what the one which we have previously simulated, tuned. Further, you can tune it. So you can just further you can increase the response. So this is what we can say. Now we have further tuned our system. Okay, and you can say the update blocks. As I said, we can get everything here, and this whatever is the final after updating, whatever is the final core you are able to see here. Here it is represented at 1 as 1 because it is the response represented for the unit step. Okay, and it has simply set or it has simply analyzed all our parameters, or according to our analysis parameter we have set this particular block, and accordingly so it will give us some initial overshoot and then 20 millimeter per second as the constant value as the output of our system after tuning this. Okay, so I have updated. I will check once. Okay. Okay, and then I'll run this one. Mhm. Okay, I'll modify the upper one. I don't know what happened here. We will just modify this and we'll try to check. Or I'll create the new file, new model, and in this I'll copy this model. Okay, so output is connected. I'll simply simulate first this one, and then we'll modify this. This is where what is happening. It's 600 by 5. This is also correct. So I need to save this model at CC2. Okay. So this is also okay. Okay, this is up to only 10. That's fine. Okay, and just change that to step input is also correct, and our scope is there. Okay, I'll just save again and I'll execute. So this is what is the expected output. I think there might be the same issue. Okay, so here we are getting the change. Now we want to compensate that change, and for that I'll just remove all these connections. I'll add PID controller. So where is the battery? I'll add this controller. So we cannot directly add here. So we need to add again the sum block. This is the block that we have obtained. Okay. So input is the expected reference one. The output will be the second input is the output, and this is connected to your PID controller, and here we need to change that sign from plus to minus. Okay, so apply. Okay, I think we finished with this. Okay, with this now we need to change only this one. After this final value expected is 20, so we are expected in this 20. I'll connect that second input to the scope as the reference point. Okay, now this has been saved, execute, and what we are getting is, so this is the response, or this is what you can observe now. This is representing, this is, it has automatically corrected the disturbances. Okay, so this is the expected value. Okay, after 10 seconds, actually you can observe here very small glitch. Okay, and this response, but initially we are getting, it is jumping to 25 suddenly, and then it is coming to the constant speed. Okay, again this jerk is not expected, so we want smooth transition, so that can be tuned using your PID controller. So is this clear? This is the expected output actually, and we are getting very good output or very good constant speed. Okay, after some seconds. Okay, I think after within 5 to 10 or 2 to 3 seconds only, your speed is getting stabilized. Okay, so actually this is very good, but suddenly it is reaching to 25 meter per second, so very high speed, and then coming back to the constant one. So this can be reduced by tuning, and the tuning can be done by simply clicking. You can manually change these things. Okay, now I'll show you by just making here this integral block also 0. We will consider only proportional block, and what will be the changes in your output. So with only proportional block, so you can see we are continuously getting, we are not getting any jerk, but we are not able to reach this 20 set value. This is the continuous steady state that we are getting with the proportional block, and here is the speed change. Okay, So with this, whatever is initial speed, it has reduced a little. So this is what is the proportional block. And by increasing that value of 1, so yesterday we have derived a formula Kp upon 1 plus Kp as the steady state error. That Kp is representing this proportional constant, which is 1 here. Okay. So that is representing actually that factor is resulting into this constant steady state error. Okay. So by just changing that value, you can reduce that one. Okay. But there is some limit. We cannot increase that value beyond certain proportional constant. Okay. So the effect of proportional we have seen. Now I'll make that as 0. I'll make this as 1. Again, we'll say apply. Okay. And we will see the output, how it is changing. So you can see here we are getting so many oscillations or the overshoots before it is going to be stabilized. And with that, again, we are not getting the stable state. It is continuously changing between two values. So we are getting continuous oscillations with the integral. Okay, we are achieving the required speed, but there exists some constant error, okay, which is in the form of oscillations. So this is the effect of integral. Okay. So again, by changing the value of 1, you can check that one. And now we'll see only this derivative constant. So it is giving us completely unwanted signal. So derivative block cannot be used, and that is why initially when we have tuned, so this value was, or it has been automatically set by the system. Okay. So these are the values. So where your proportional and integral constant is playing major role to get the required speed. Okay, again, so we have obtained this. This is the required speed. Okay. So further, I can reduce this overshoot by tuning. Okay. If you are not able to manually recite the values, there is an option called as tune, where, as I initially just shown, so this is representing your response of the system, the current response of the system. You can obtain all these waveforms from add plot. If the plot is not visible, you have to click on this add plot. So we are analyzing that in time domain, not in frequency domain. So time domain. And just here you can observe the current block parameters and tune parameters, and accordingly you can reduce. Now we have to here the overshoot has been reduced, but response time has increased. So that response time can be reduced by just using this slider. Okay. So this is something better. There is smooth transition we are getting instead of sudden jerk. Okay. So depending on the application, you can set your system to the previously tuned values 110, or these are the tuned. So if I say update, both will change, and this response now will check at our system. Okay. So here I'll run it again because we have tuned that PID, and this is what you are able to observe. So this, which was reaching to 25, has reduced, and here we are getting little glitch. Okay. So this is how you can tune your system. Not necessarily it should be the vehicle model. It can be any model that you are considering. Okay. So with this, if you're having any doubts, you can ask. Okay. So are you able to just understood? I saw that message of Ishita. So I have completed my explanation. Now, if anybody is having any doubts, or if you are not able to see or just coordinate these things, audio, video, then I need to make another recording and I'll share with you. Any doubts in this? Yes,
No, ma'am.
hear me. Hello. Okay, if you're having any doubts, you can ask. I'll check the video quality. If video is clear, then you can refer that video if you are having any problem to listen or to just understand this particular experiment. Okay. With this, I think this we have completed our fourth experiment, and the modeling and role of PID controller is very much clear from this particular experiment, and how your cruise system will work, that is also clear from this particular experiment, I think. Still, if you're having any doubts, you can post your messages on WhatsApp or this team. Okay. So I'll download the attendance and then you may leave. Okay, I'll stop the meeting. I'll end the meeting. Okay. काय झालं काय माहिती.